Good morning. Welcome to Ray Summit 2025. Yeah, let's go. It's our fourth summit, so welcome back to those who have been here before, and a warm welcome to everyone that are here for the first time. Last year, when I attended my first Ray Summit, I had the opportunity to interact with a lot of you, and one quote stood out for me. Of all the conferences I've attended, this is the most concentrated gathering of AI and ML professionals that directly impact what I do every day. This was a direct quote coming from one of the senior attendees here in the audience. It's been a year since we met, and what a year it's been. Let's start by taking a look at the evolution of computing. We have had many eras, starting with the mainframe, going to client-server and enterprise computing, to the internet and web services, to cloud computing, and now the era of AI. Each era was unlocked by increasingly precise control of bits at larger and larger scales. AI is the next era, affecting everything from media to finance, from robotics to coding to search, self-driving, finance, space, pretty much everything. Make no mistake, the AI era is definitely here. As we look at the evolution of computing, each era was built on its own stack, on a new compute stack with a compute engine that powered that era. Starting with client-server and enterprise computing, the compute engine was a server powered by the likes of the Windows server or a Unix server, and there were many variations of that, Oracle databases and the like. Then came the internet and the web services era, where we had to virtualize the server into VMs to scale out. And on top of these VMs, we built the LAMP stack, as we affectionately called it back then. Linux, Apache, MySQL, and PHP. And then came the mobile cloud era, the cloud computing era, which was driven by microservices and big data. Here we added the container as the compute engine, and on top of that, we built services like Kubernetes, Kafka, Spark, Redis, MongoDB. I could go on. There's so much infrastructure software that was built in this era and still powers a lot of our platforms. But these transitions, while they look simple, were anything but. They were extremely disruptive. And many a times, many companies faded into the background because they were unable to navigate these transitions well. What separated the winners from the losers was how quickly you were able to adapt to this new paradigm and then build the infrastructure that powered this new paradigm. Names like Amazon that disrupted the art of selling books, or Netflix that disrupted how we watched movies, Uber that disrupted the traffic industry, the taxi industry, and Robinhood that disrupted how brokerage was done. These are just a few examples, and there's many more. And to be sure, these were great names too. They were not also-rans. They were real big brands of their time. The trap tends to be that what you have done, what got you here, is what is going to get you to the next level. You hear things like lift and shift as a very common term. I have invested a lot of time, money, energy, talent in building what I've built already that's powering my stack. Why do I not take that and move it forward? Unfortunately, that never works out well. We saw that in the data center, taking lift and shift data center apps to the cloud, that didn't work. Moving desktop apps to mobile, that didn't work either. Running analytics on BI tools, that didn't work either. These are all examples of why taking an existing stack and trying to adapt it to the new era doesn't work. And the AI era will be no different. It will drive significant change and drive eventually its own computing stack. Here are the core fundamental reasons why. Number one, AI is built on heterogeneous hardware. It's not just about CPUs. It's CPUs and accelerators that come together to create your hardware layer. And increasingly, these accelerators are getting more and more powerful. They're getting interconnected with high-speed networking technologies like InfiniBand and Ultra Ethernet. They're enabling technologies like RDMA to really allow very fast context transfers between GPUs and TPUs and so on. And finally, the build-out of purpose-built specialized AI data centers is driving the AI-native computing era. Built on top of these are AI processing pipelines. Historically, we looked at pipelines like this. Data processing was a CPU pipeline. Training was a primarily GPU pipeline. And serving or inference was a matter of taking the model, hosting it on a single node GPU, and serving it out, and scaling it out as you would a microservice. What's happening now with the advent of multimodal data processing is the data processing itself is becoming a heterogeneous workload. Training, which used to be about pre-training a model, is now giving rise to the era of post-training and reinforcement learning, which is also becoming a heterogeneous workload. And serving is evolving from a single node GPU workload to a multi-node, much more complex distributed inference workload with the rise of reasoning and agentic AI. The models themselves, because of the scaling laws, are improving every day. It seems like there's a new model being released every day with increasingly more powerful capabilities. And these models are going to be at the heart of everything we do in the AI computing era. And finally, the way we build our systems is changing. Until now, all the systems we built were what you could consider deterministic systems. We would write our logic into code, create our microservice, perfect it, give it to prod, and then let prod takes it from there and gets it deployed. And then we move on to the next microservice. Well, AI is not like that. The heart of AI, as I said, is a model that is fundamentally non-deterministic in nature, which means once you put the model in production and start using it, you have to monitor it constantly. The words that come up a lot is evaluations. Alignment. Is the model performing in alignment with your goals that you set it out for? And evaluations are the way that you monitor models and their behavior. So it's not just a model of, it's not just about perfecting your code and shipping it. It's about constantly monitoring and ensuring that the outcomes are being delivered that you desire. It's about keeping that circle between data, code, and models going at all times. And the most important thing, the superpower that you must develop, is the ability to move fast. Iteration velocity is the name of the game here. And these four core drivers is what driving the emergence of a new AI computing stack. The core requirements for these, first is to be able to take the fundamental requirements of these workloads, the many parallel tasks that you need to run in real time, and dynamically orchestrate that across a cluster of CPUs, GPUs, and so on. Second, you need to have the flexibility in the compute engine to not only handle your workloads of today, but the workloads of tomorrow, to be able to evolve. Third, you need the fault tolerance to be able to run large jobs and services. Training runs can take weeks. Large batch inference jobs can take days. And you don't want these jobs to be interrupted. You want the fault tolerance in your compute fabric to be built in to ensure they continue at all times. And finally, the language of AI is Python. So any compute infrastructure that you address and scale and orchestrate needs to be Pythonic. This is what Ray was built for from the ground up. When Jan, Robert, and Philip started experimenting with reinforcement learning in their labs in UC Berkeley, the inspiration was this. And Ray is now, thanks to their efforts and the efforts of the community here at large, is firmly embedding itself as the compute engine of this AI native stack, powering not only AI workloads, but being the focal point integrating AI frameworks like PyTorch and vLLM and SGLang and many more. If you think of the evolution now, there is a new stack forming for AI native computing, and Ray is at the heart of it. This is why the downloads for Ray accelerated dramatically this year. Just this year alone, we have seen the number of downloads increase 5x. And it's because the workloads are getting more complex. It's a recognition of the reality that you need to build an AI compute engine that facilitates the new. All of you obviously have a huge hand in this. So I want to take a moment and thank you. We all feel deeply, deeply grateful at Anyscale and are humbled by the work and the inspiration that you bring every day and create amazing solutions using Ray at the heart of it. I want to take a moment and talk about a few examples. First, Grok. xAI is using Ray to build their models. Multimodal data is central to their effort, and they have built scalable high-performance data processing stacks using Ray Core to scale image and video data processing at massive scale in a fault-tolerant manner. xAI will be speaking about how they scale batch inference and multimodal data processing with lots and massive quantities of image and video data to prepare their training data. Next is Cursor. Cursor is building their leading agentic coding platform using Ray. Doing this involves scaling data processing, agents, evals, and reinforcement learning. They will talk about their stack, how Ray powers their infrastructure, and how they built their most advanced models. From the world of coding to the physical world, physical intelligence is a leader in building AI for robotics. Building AI for the physical world involves scaling data collection in the real world using large quantities of data, video data, robotic sensor data, and processing that to train these models. They'll be sharing how they build their generalist policies that can perform across different robotic embodiments and unstructured environments. So the big question in front of all of us is, how will you build your AI stack? The choices are straightforward. Option one, you could continue to extend the stack you already have. Option two is to build on top of frontier models. And option three is to create your own AI native infrastructure stack. Option one, as I discussed earlier, is about the innovator's dilemma. It seems very appealing because you already put a lot of investment into it. But by extending it, you lose the dynamism that you need to be able to orchestrate fine-grained tasks across a heterogeneous compute cluster, which basically means you start to underutilize your hardware, which are expensive investments, and most importantly, you won't be able to scale up for these new workloads, multimodal data processing, reinforcement learning, and distributed inference. The other option, which is to build on top of frontier models exclusively, is also limiting because you won't be able to tune these models for your specialized use cases. And that is what you truly need to do to deliver value to your organizations. Scaling lots of data, building agentic systems that use multiple models, all coming together. And to me, I think the most important reason is these transitions are an opportunity to build expertise, which is at the heart of navigating these transitions successfully. Every company, I remember the day when microservices came out, and we all thought that's only for the super high-tech companies. My software needs don't need microservices. Yet today, you can't find a software application builder that doesn't build using microservices. That same idea holds true for AI as well. You will be building AI, and it's important to build AI skills within the organizations. So the only real option then is about building an AI platform. But the question is how? I talked about Ray. Ray is at the heart of it, but there's a lot more to it. You need, of course, the cloud infrastructure, the compute hardware, and the frameworks that go with it. And then you need to bring it all together. You need to integrate this platform with frontier and custom models. You need to incorporate your dependencies, tooling for your developers. You need to boost performance. You need to make sure enterprise security policies are held together. Governance becomes important, especially with large teams. And finally, you got to be able to deploy in your cloud. This is what a unified AI platform is supposed to do. And that is our mission at Anyscale, to build out a unified AI platform that empowers every team to become an AI team and every developer to be an AI developer. Next, I'd like to bring Jon Stoika up to share with you a little bit about the founding origin story of Ray, as well as talk about why Ray's time is now. Please welcome Jon.
Please welcome to the stage Jon Stoika, co-founder and executive chairman of Anyscale.
Thank you, Keerti. Good morning, everyone. Thanks for coming. So next, I am going to tell you a story, the Ray story. It all started in fall of 2015 when two machine learning students, Philip and Robert, decided to take my class on big data systems. And they decided to do so because they wanted to learn how to build tools for their own research, because the tools at that time were hard to use and did not scale. And here is me with Philip and Robert, less than 1 year later, doing what any typical advisor does best: hands in pockets, interrupting students from doing work with annoying questions. At that time, if you remember, there was a lot of excitement around reinforcement learning. DeepMind and OpenAI demonstrated that RL can play computer games at the expert level and beyond. Google showed that RL can reduce the energy for cooling in data center by 40%. And of course, in 2017, AlphaGo shook the world by beating the Go world champion. And we are doing RL research ourselves. Philip co-authored with John Schulman, co-founder of OpenAI, a highly influential paper on Trusted Region Policy Optimization, or TRPO. TRPO is the ancestor of some of the most popular RL algorithms, including PPO and GRPO. And we are using RL for various applications, like teaching humanoid robots how to walk, improving traffic congestion, optimize database queries, and much more. So naturally, we build Ray for RL to support our own research. And here is RLlib, the library we built on top of Ray for scaling RL, the most complex workload at that time. Eventually, RLlib went to become the most popular RL libraries. But we are ahead of our time. While powering impressive applications, RL was slow to catch up. Fortunately, RL is such a general workload that building Ray for RL meant that it could support almost any AI workload. And here are the three canonical workloads powering AI: data processing, training, and serving, like Keerti mentioned. And there are three stages in the evolution of these workloads in the inceptions of Ray that have shaped the Ray's impact and adoption. And the three stages are classic deep neural networks and two phases of generative AI. The first stage involved dense neural models that typically process logs, such as user logs, to power applications such as recommendation systems. Data processing was embarrassingly parallel, primarily using CPUs. The models were small enough they could fit on a single GPU, so training used mainly data parallelisms to scale. And during inference, the main challenge was replicating the model on multiple GPUs to handle high request loads. Thus, while these workloads were distributed, they were relatively simple and moderate in scale, typically running on tens to hundreds of machines. As such, these workloads made limited use of Ray's full power and generality. And this was reflected in Ray adoption, which grew steadily but relatively slowly, taking 6 years to reach 500K downloads per week. The second stage, which we call the first generative AI phase, is defined by the release of ChatGPT nearly 3 years ago. And this stage kicked in the pre-training scaling law, which simply states that more data, larger models, and more compute predictably improve model performance. So no surprise that during this stage, we've seen a dramatic increasing in scale. Accordingly, the scale of data processing increased, though this workload was still confined to CPUs. And as models become larger, so they could no longer fit on a single GPUs. And as a result, new parallelism techniques emerge, such as tensor parallelism, to scale training. That said, most models, especially open source ones, were still small enough to fit on a single machine with multiple GPUs, which meant that the main challenge for inference remained to replicate these models on multiple machines to handle high request workloads. So in summary, during this stage, the workloads grew moderately in complexity, but dramatically in scale. This made Ray more relevant. For example, OpenAI used Ray as part of their stack to train ChatGPT. And this was reflected in Ray's adoption, which accelerated, growing from 500K to 1.5 million downloads per week in just 2 years. However, by the end of 2024, the scaling law of pre-training has slowed down. And in response, researchers turned their attention to post-training to further advance large language models. And this is a famous plot from the launching blog of O1, which shows that post-training, in this case reinforcement learning, can be as effective as improving model performance as pre-training. And we refer to this stage as the second phase of generative AI. In addition to post-training in this stage, we witness the rise of multimodal models that handle not only text, but video, images, and audio. And pre-training and multimodality together have driven a massive increase in complexity of the workloads. Data processing is no longer CPU only. It now uses a combination of CPUs and GPUs. Model architectures have become more complex with the emergence of a mixture of experts. Many models are no longer fitting on a single node. And this drove the number of parallelism techniques to scale up the training. Last time when I checked, there were no less than 7 different parallelism techniques. On top of that, inference adds more complexity with techniques such as expert routing, prefield disaggregation, speculative decoding, and more. Now, this is the complexity we build Ray for. The more complex the workload, the more Ray shines. And this is reflected in Ray's adoptions, with downloads exploding, growing nearly 5 times over the last year alone. So not surprisingly, today, Ray dominates some of the most demanding workloads. One example is multimodal data processing, which combines pre-training, post-training, and inference. Each of these stages have their different demands on compute and I/O. Pre-processing and post-processing typically works best on CPUs, while inference on GPUs. So fundamentally here, you need to run this workload on a large-scale heterogeneous cluster. Very complex. But Ray handles this complexity for you. And with the rise of multimodal data, like images, video, and audio, things are even more complex. Now the pre-processing and post-processing themselves might require some mix of CPU and GPUs. Again, Ray handles this additional complexity for you. The inference itself is becoming more complex, as I mentioned, with mixture of experts models. Different experts can run on different GPUs. With prefill disaggregation, tokens from the same request may spawn both CPUs and GPUs. And again, they can handle this additional complexity for you. And finally, we are coming full circle. Like I mentioned, one of the largest and most important workloads today is post-training. And the key component of post-training is reinforcement learning. And since we initially built Ray for RL, it should come as no surprise that today nearly every open source post-training framework is built on top of Ray. So, Ray's time has finally arrived. Ray's time is now. Next, please join me to welcome Robert, co-creator of Ray and co-founder of Anyscale, who will tell us about how Ray fits in the modern AI stack and will make several exciting announcements.
Please welcome to the stage Robert Nishihara, co-founder of Anyscale.
Thank you. Thank you, Jan. So Jan and Keerti talked about how complex AI workloads have grown with reinforcement learning, multimodal data, distributed inference. And they also talked about how complex hardware has grown with greater scale, heterogeneity, and failure rates. The sheer complexity at both the top and bottom of this picture have given rise to the need for a software stack that sits in between and connects the applications to the hardware. That software stack has to solve a huge range of challenges, ranging from scale to reliability. We've worked with hundreds of companies who are building out their AI infrastructure and have seen common patterns and common layers emerge in this stack. So I'd like to share the different layers that we've seen. At the top is the training and inference framework. This layer is responsible for running the model efficiently on the GPU. PyTorch is the dominant deep learning framework, and there's a rich ecosystem around PyTorch for parallelism strategies and transformers. But fundamentally, this layer is responsible for squeezing the most performance out of the GPU. Next is the distributed compute engine. This is where Ray sits. This layer is responsible for solving the hard distributed systems challenges of scaling. That includes process coordination and process management. Includes data ingest and data movement, failure handling, auto-scaling, resource management. All of this typically runs on top of a container orchestrator like Kubernetes, which is responsible for provisioning compute and handling coarse-grained multi-tenancy. So think user-level and job-level multi-tenancy. Now, as these layers have emerged, they've also been co-evolving with each other. And I'll give a couple examples. Jan talked about how complex distributed inference has become. Doing a great job with large model inference, it's such a hard problem. It requires doing a good job at multiple different levels of this stack. In particular, doing a great job with the inference engine and with process coordination. So the Ray and vLLM open source communities have worked very closely together to enable fine-grained placement of vLLM workers. So this has been essential for enabling cross-node parallelism strategies, prefill decode disaggregation, prefix-aware routing, wide expert parallelism, and a number of performance-critical optimizations. The Ray and Kubernetes open source communities have collaborated to enable new features like vertical pod auto-scaling for Ray workloads and more fine-grained application-level resource isolation. The reason these features require you to work at multiple levels of the stack is that they combine Ray's fine-grained awareness of what's happening inside of the workload with Kubernetes' ability to manage containers that are running the workload. So these are just two examples. The need for this software stack has grown a tremendous amount over the last year. So for that reason, Jan and Philip and I are very excited that Ray is joining the PyTorch Foundation. When we, yeah, thank you. So the PyTorch Foundation is home to foundational AI infrastructure projects. And when we started Ray back at UC Berkeley, from the very start, we conceived of Ray as a community-based open source project. So we're very excited to collaborate with the rest of the open source AI infrastructure ecosystem and really build out this stack. Next, I'd like to share a little bit about what the Ray community has been up to recently. So we've done a huge amount recently. We've merged 5,000 PRs in the last year. This is double the daily rate from the previous year. I'm going to start with Ray Core, because Ray Core is the foundation of the Ray ecosystem. What's changed is that over the last year, people have been running Ray at larger and larger scales. Not just at larger scale, but with less reliable hardware. That could mean spot instance preemptions, GPU failures, node preemptions, container preemptions. And not only instance failures, but networking failures. People are running Ray across multiple zones in situations with unreliable networking. And so RPCs can fail, TCP connections can be dropped, servers can be temporarily unreachable. Because of this is now the norm. Because of this, we've invested heavily in reliability at scale for Ray. What does that mean? We've hardened Ray's failure handling across the board. That includes making the Ray internal state machine idempotent, so it can handle retries at any point. We've invested in isolating Ray system processes from application resource pressure. Right? That's essential for reliability. And we've built a scalable observability stack. We've created an event export framework, so users can write events directly to persistent storage, which is necessary to remove the global control store bottleneck. So these are examples of things we've been doing. Reliability at scale has been a core theme. The other core theme I want to talk about is performance. We've seen a huge need recently for direct, accelerated GPU to GPU object transfer. This is important for reinforcement learning, where it comes up you need to synchronize ship weights from training workers to inference workers very rapidly. It comes up in distributed inference for KV cache tensor transfers. It comes up in distributed training, especially really complex scenarios like non-uniform sharding of large multimodal models, where you need to ship activations and gradients around between different worker pools. And it also comes up in data processing for GPU to GPU data ingest and multi-stage data processing with large tensors. So this comes up all over the place, and this has to be really fast. So to support these workloads, I'm very excited to announce native RDMA support for Ray. Ray Direct Transport supports point-to-point transfer of PyTorch tensors between Ray actors. And we have a deep dive on this later today, which I encourage you all to attend. This supports RDMA-based backends, and it also supports collective-based backends. So to illustrate this feature, I want to actually show what it looks like in code. And to show it in code, I'm actually going to take a detour and first introduce the Ray Actor API, and then build up an example that uses this. So I'm going to show this through a reinforcement learning example. We've got two classes, a trainer for training the model, and a generator for generating new data using that model. And we need to synchronize the weights. So we have get weights and set weights methods. And Ray, at its core, is an actor framework. So it lets you add this ray.remote decorator. And now when I instantiate one of these classes, it creates a new actor process somewhere in the cluster with the appropriate compute resources. And you can start one of these. You can start 100,000 of these. They can invoke methods on each other, talk to each other. And with relatively little code, you have the building blocks for interesting distributed applications. So now to actually do reinforcement learning, we've got a couple parts. We're going to alternate between training the model and then generating new data. And to do that, we call train.remote and generate.remote, and that will kick off, send RPCs to the actors and kick off the methods. And in between, we're shipping the weights from the trainer to the generator by calling getWeights.remote on the trainer, and then there's an object reference, which is essentially a future, passing that into set weights. So the way this code is written here, the weights need to first be transferred to CPU memory and then shipped over the network. And depending on our use case, if we're running at scale, if we're using a large model, that's likely too slow. What we can do with Ray Direct Transport is add this line here, specify the transport backend, and now the weights will be shipped directly from GPU to GPU via RDMA. So improved RDMA support is super, super important for Ray. This is a direction I'm very excited about, something I'm excited for you all to try out, and an area we're excited to collaborate with the open source community on. Next, I want to share a little bit about the Ray libraries. And I'll talk about two different recent developments. First is the importance of multimodal data. We've seen an explosion of multimodal data over the last year. And we've invested in making Ray data the most powerful multimodal data processing engine. Right? That includes great handling of large tensors, handling of large cross-node multimodal models for batch inference, heterogeneous data types, and purpose-built multimodal data formats. And doing this has led to significantly improved faster reads and higher throughput for aggregation, complex aggregation-heavy workloads. Right? So there's a tremendous amount of work going on here, and we think multimodal data is just getting started. The second development I want to share is something everyone here knows, which is the growth in model size. And this is what has led us to invest in shipping a huge range of features to better support large model inference, ranging from prefill, decode disaggregation, prefix and LLM-aware routing, custom auto-scaling, wide expert parallelism serving patterns, and a huge range of other optimizations for both online and offline inference. And I expect these two trends to just continue. But these are just two examples of what we've been up to. I'm not going to list everything, but we have 8 deep dives at this conference today and tomorrow covering the Ray internals, the roadmap, and what the team has been up to recently. The last thing I want to call out is that there is a rich ecosystem on top of Ray. You've probably heard of a number of these different projects. We've seen an explosion of new projects, ranging from AI Bricks from ByteDance, to Nemo Curator from NVIDIA, to Slime from Z.AI. These are RL frameworks, agent frameworks, inference frameworks, data frameworks. Many of these projects will be speaking here today and tomorrow, and these teams are doing incredible work. And this is what makes Ray powerful. It's the presence of such a rich community ecosystem on top of Ray. So thank you. Next, I'd like to invite Keerti back to the stage to talk about the Anyscale platform.
Excellent. Well, next I want to change hats and move from open source to Anyscale. As I mentioned earlier, the requirements for an AI platform are beyond the stack. You, of course, need the stack itself, but you need to be able to productize the stack, which means integrating your models, incorporating your dependencies, creating your developer tooling, boosting performance, security policies, governance, deployments, and more. And this is what we built Anyscale for, to be the unified AI platform that empowers you to go make your AI models, your AI products come to life. Thanks to our adoption from our community, you have embraced Anyscale very warmly, and I'm very excited to announce that Anyscale has grown 10x in revenues over the last 8 quarters. And these are just a few example customers that we are showing here on the slide. I want to take a moment to walk you through 3 key examples. First is TripAdvisor. Many of you probably use TripAdvisor to plan your trips. They use customer images and vast amounts of it in a batch inference mode to then feed their recommendation engines when you do your searches. Those 2 stages were disparate before. The batch inference stage was done differently than the online inference part of it. With Anyscale, they were able to unify both of those stages together and lower the cost of batch embeddings by 70% and reduce their code sprawl by 80%, really modernizing their inference platform within TripAdvisor. Coactive is a startup. They're a multimodal intelligence platform for media companies. And they used to take weeks to be able to transition from development to production. And with Anyscale, they were able to reduce that time to a single day, to take something that they developed and put it in production. And using Anyscale, they were able to lower their costs by 4 times and GPU compute costs by 75%. Nubank, which is a large bank operating out of Latin America, they are transitioning to an AI-first future for their customers. They use Ray Train and Ray Data on Anyscale to train their own internal transformer model. They are transforming their own company from that cloud-native company to an AI-first company and delivering superior experiences for their customers using their transformer models. So these are just a few examples of how customers are embracing Anyscale. We'll dive deeper into the platform and some exciting new announcements coming up on the Anyscale platform. To do that, let's welcome Jaikumar Ganesh, Head of Engineering, up here.
Please welcome to the stage Jaikumar Ganesh, Head of Engineering at Anyscale.
Thank you, Keerti. How's everyone doing? Race time is now. I want to amp it up further. Please stand up. All right. So on a count of 3, 2, 1, we are all going to say, let's go, Ray. 3, 2, 1. Let's go, Ray. Right. Once again, louder. 3, 2, 1. Let's go, Ray. That's the spirit. Let's go, Ray. Please take a seat. So Keerti talked about the impact customers like TripAdvisor, Coactive, and Nubank are having with the Anyscale platform. So what is this Anyscale platform? It primarily consists of these 3 main layers: Developer Central, Ray, and Cluster Controller. We have worked with many Ray users and Anyscale customers, and we have a clear idea of the Ray adoption journey. Getting started with Ray is very easy. You just download Ray on your laptop, and you're up and running. But when you go into multi-node development, challenges start to appear. You now need to propagate dependencies to all the nodes of the cluster. You need observability. You need monitoring. You need debugging tools to figure out all the worker logs in all the nodes. And then you have taken this workload to production. And when you go to production, you need to handle all the clusters. You need to upgrade them. You need to understand the cloud provider stack. You need monitoring. And when you have a workload that's running, you want it to be fast. You want it to be cheap. You want to be reliable at scale. And once you're there, you want to expand Ray usage to all other teams within your company. That's not easy. You need to first train them on Ray. Then you need to take care of cost controls, governance features, audits, budgets. You need a way to track all your model versions. You started with Ray. You learned Ray. Now you have to solve all the problems around Ray. That's not easy. That's why we built Anyscale, fully managed, production-ready platform. But the beauty of Anyscale comes in when all these 3 layers work in unison together. That's the magic. What do I mean by that? Let's take an example. You have a training workload. You're training a model across thousands of GPUs. You need observability to deeply profile GPU metrics. You need a job framework to kick off your training workload. You need checkpointing and mid-epoch resumption so that when your train job fails, it can restart from the same point. Your infrastructure needs to provide GPU health checks so that it can get rid of all the bad GPUs from the cluster. You need capabilities like GPU search capabilities in multi-cloud and multi-region so that you get the best GPUs. It's all these 3 layers working together that's going to power your platform. Let's take 2 customer examples. Geotab, an AI-first fleet company. They use large amount of video processing data to improve driving behavior, optimizing fuel efficiency, and road safety. They weren't able to find any system that is going to serve their needs. So they used all the 3 layers of the Anyscale tech stack: observability, the runtime, the cluster controller layer. They were able to see 43x better throughput, 40% reduction of GPUs at peak. Prenovo, another AI-first preventative healthcare startup. They want to collect a lot of multimodal data, petabytes, and they want to do anomaly detection, biomarker correlation. They also used all the 3 layers of the tech stack: observability, the runtime, cluster controller. Developer startup time improved by 5x, and they were able to reduce costs by 40%. They were able to do this at petabyte scale and also handle the security and compliance needs of the health sector on the Anyscale platform. That's the power of Anyscale, the 3 layers working together. So now let's deep dive into each one of these layers. Let's start with the Anyscale runtime. What's this Anyscale runtime? Firstly, it's fully compatible with Ray open source APIs. If you have an application working in open source, it's going to work on Anyscale. It's an evolution of the project we announced last year called Ray Turbo. We battle tested it, made it more reliable, worked with all the customers, and made your workloads faster, cheaper, and reliable at scale. We worked every stage of the pipeline, from reading of data to auto-scaling to checkpointing. But all of you are developers and engineers. You're not going to trust me. You'll say, show me the benchmarks. To do that, I'd like to invite Richard Liao onto the stage.
Please welcome to the stage Richard Liao, founding engineer and product manager at Anyscale.
Thanks, Jay Kumar. Last year, we announced Ray Turbo. And this year, we're evolving Ray Turbo into Anyscale Runtime. In Anyscale Runtime, we've optimized the 3 canonical workloads that Jan talked about: data workloads, training workloads, and serving workloads. Now let's deep dive into each, starting with data. Great models require great data, and great data requires great data processing. Data processing workloads for AI often have unique requirements. First of all, they need to maximize throughput. They also need to work with multimodal data, which includes structured data, images, videos, text, audio, so on and so forth. And finally, they also need to work with the great accelerator ecosystem that we have today, including CPUs, GPUs, but also TPUs and other chips as well. And we've optimized Anyscale Runtime's Ray data to address these requirements. Within Anyscale Runtime for Ray data, we've improved data reading and writing for key data formats, including Parquet and JSON. We've re-implemented various operations to take advantage of vectorized compute kernels. We've re-implemented our autoscaler so that it can be much more responsive and better efficient. These changes can lead to significant performance improvements over open source Ray. Let's take a look at how this impacts some customer workloads. A couple customers we worked with had multiple terabytes of data stored in their data lake of images. And these pipelines were fairly similar. They would read the data, transform it on CPUs, run the inference using a vision language model on GPUs, and finally write the results back into storage. And what we did was we compared this, running the same exact pipeline using open source Ray and Anyscale Runtime. On a fixed capacity cluster, running the same pipeline on Anyscale Runtime delivered about 2x faster performance compared to open source. Then we enabled our optimized autoscaler in Anyscale Runtime, and that single change made the run 6x more cost efficient without any tuning or manual intervention. So you might say, okay, well, this is a very specific workload, but we also took other common workloads, and we saw similar performance enhancements. Anyscale Runtime was measured to be about 10 times faster for select feature preprocessing workloads. Anyscale Runtime was measured to be 2.5 times faster for select TPCH queries. Now, beyond data, Anyscale Runtime also has major features for training reliability as well. Training workloads are very notoriously hard to scale well, especially when you have GPUs that fail all the time and data loading that can be really prone to out-of-memory issues. And Anyscale Runtime addresses these exact problems. With dynamic memory management, Anyscale Runtime can automatically set task memory requirements, reducing spilling and out-of-memory issues for training data loading. With mid-epoch resumption, Anyscale Runtime enables you to pause and resume training when you're using large data sets. Elastic training allows training to continue even under preemptive nodes. And GPU profiling on Anyscale Runtime provides in-depth observability into accelerator health and utilization. This, in conjunction with all the other parts of the Anyscale stack, solves many training reliability issues that we see in production. Now, let's take a look at serving and online inferencing as well. Online inferencing systems have a unique set of requirements. And in particular, compared to any other workload, SLAs are key. However, as online inferencing systems continue to evolve, they also need to handle multimodal data, and they also need to handle heterogeneous hardware. And to solve these issues, the team has optimized critical parts of the Anyscale Runtime serving stack as well. In Anyscale Runtime, we've implemented a faster transport layer for large object transfers. We've optimized our ingress layer to improve scalability and throughput, and we've implemented replica compaction for efficient and cost-effective autoscaling. Let's see what this means for real-world serving pipelines. So working with customers, we've seen multiple pipelines that leverage both CPUs and GPUs for online inferencing with models. And taking a representative pipeline that we've worked on with some select customers, Anyscale Runtime was able to achieve 7x higher throughput on the same hardware and latency constraints compared to open source. I've talked about a couple of these workloads in depth, but Anyscale Runtime is actually much more broad and much more deep than what I can cover here. We've done optimization work across a wide variety of AI workloads, working up and down the stack. And you can find out more about this and reproduce the results on our GitHub. We also have a roadmap for many more critical workloads. And our goal for Anyscale Runtime is to be the best compute substrate for any AI workloads out there. Now, to show you how easy it is to use this very, very powerful runtime with all the great developer tooling that we have on Anyscale, let's hear it from Goku and Akshay.
Please welcome to the stage Goku Mohandas from Ray Noob and Akshay Malik, Ray Expert.
Yo, Akshay. So I'm a Python application developer and honestly a bit of a Ray noob as well. And I've been wanting to build this agentic application where I can ask any question I want about any kind of video, a trailer or an entire movie. And I started to build it out, and I already started to hit a bunch of bottlenecks. There's so many different models I need to use that don't fit on my machine. And even just a few minutes of video involves tens of thousands of frames. Do you think you can help me build it and also scale it out?
Yeah, of course. I'm a big-time Ray expert, as they just said. So I can definitely help you out here. Tell me more about your application.
OK, so here's the super high-level architecture. I want to start off with some pre-processing. So let's say we start with a video, and I want to be able to extract the audio and also the visual frames. Then I want to kick a whole series of batch inference workloads where I take the audio, generate transcripts, and also embed those transcripts so we can search semantically. And I want to do something similar for the visual frames as well. Finally, I want to have some kind of agentic workflow on top because some questions maybe just require the transcript, some just the video, and some maybe multimodal and requires everything. Now, how do we build this and actually scale it out?
So I actually had the foresight that you would be asking me this
really?
exact question during the keynote today. So I built out Rayflix for you. Let's give it a go.
OK, I was actually just backstage, and I was talking to Jan, our visionary founder, and he was just telling me about this next big thing, K-pop demon hunters.
Jan said that.
Yeah, he was really into it. So I don't really like scary movies, so are there actually real demons in this movie?
Let's test that out.
I mean, it's meant for children, but let's see. Yikes.
Looks like there's some real
OK,
demons.
so it looks like both the transcript and video found matches. I think I'm going to give it a shot anyway, because Jan usually has a good intuition for these kind of things.
Yeah, you should.
Okay, so I want to ask a bunch more questions about some of my other favorite movies, but maybe you can first tell me about how you did this. How did you scale this? Where did you build it? How did you put this together?
Yeah, so I started in Anyscale workspaces. So Ray always had like a laptop-friendly development experience in mind, but with Anyscale workspaces, we can create this infinite laptop experience seamlessly on any cloud. So here I have my dependency management, my Ray data code, and really everything I need to develop and debug at scale.
Nice, and then just double checking, but did you get all of my thousands of videos from Azure Blob Storage, metadata from Unity Catalog, and data from everywhere else too?
Yeah, you should trust me, bro. So Ray data can read from virtually any data source. And on Anyscale, we have these easy one-click integrations into popular data catalogs like Databricks, Snowflake, or really wherever your data is being held hostage.
Okay, so this sounds pretty cool. Now, I know you're a Ray expert, but I've heard that working with distributed systems is not only hard, but extremely difficult to debug. Are you telling me that nothing went wrong during all this?
I messed up a few times, but with Anyscale observability tools, I could figure out exactly what was going on. So metrics, logs, tracing, all in one place. There was also this really cool Ray data dashboard. So this gave me contextualized information for Ray data workloads. So I can see my execution graph here. I can see the throughput, the errors at each stage. So I can really optimize my Ray data pipelines.
Nice. This looks extremely comprehensive, but it also looks like a ton of information thrown at me at once. How do you know where to look when something specific happens, like, say, an out-of-memory issue?
Yeah, Anyscale has thought through that too. So there's these critical events that show up. So things like out-of-memory errors, failed nodes, and then I can click on this and get some guided fixes on them.
Nice. Okay, I get a pretty good idea of how you developed and debugged this, but how did you go from here to actually kicking off all the different batch inference workloads on top of the thousands of videos?
I used Anyscale jobs. So with Anyscale jobs, think of them as ephemeral Ray clusters. I can schedule jobs. I can integrate with any orchestration tooling of my choice as well. So I can really scale out my data processing.
Okay, and these jobs, though, don't they have a ton of different artifacts? For starters, we've loaded data from so many different places. We're using so many models for the batch inference, like Whisper and Clip. And obviously, we're generating a lot of transcripts and embeddings. How do you keep track of all these different artifacts?
Yeah, it got a little tricky, to be honest, to track all these different data sets and models. So today, we are launching lineage tracking on Anyscale.
That sounds like a pretty big deal, to know out of the box where your data models are coming from and where they're being used.
Yeah, it is such a big deal that we have to move to a big slide. There we go. So with lineage tracking, we can track all model and data transformations automatically. So that V3 final model that you kind of YOLO shipped to prod last week, I know exactly what data went into it.
Just to be clear, I don't name my models, that kind of stuff.
No one should.
Okay, so this is very cool. And I get how you did the pre-processing, add batch inference using a combination of workspaces, jobs, and some of the awesome tooling. But what about the real-time service, though? I feel this is almost a little too complex to even architect. So I want to start with the query. I want to serve an open source LLM that can look at the query and come up with a series of actions or plan. And each of these actions basically are independent tool calls. And think of them as retrievals on top of the data that we just generated from the batch inference. So ability to search through the transcripts, search through the visual frames, and even some multimodal logic as well. And then I want the same original LLM to use the outputs of these tool calls to generate the response. How do you build something like this? And then am I going to get some kind of ridiculously large bill for all the idle GPUs that you've involved?
No GPUs were wasted in this production. So with RayServe, I can easily convert these different components that need to scale independently into RayServe deployments, and then I can deploy it all together as part of one application.
Nice, and then you were able to incorporate that agentic logic as well?
Yeah, absolutely. I can build my own dynamic inference graph all in Python in one place. And then I even took it to production using Anyscale services. So think of Anyscale services as this like fully production-ready endpoint. So it gives me things like zero downtime upgrades, observability, A/B testing. It gives me complete peace of mind in production.
OK. Actually, I've got to say, I think I'm pretty convinced that Ray is extremely powerful. But I still feel, at least even without the help of a self-proclaimed Ray expert like yourself, I'm going to be pretty overwhelmed still, converting my workloads to Ray, debugging them, and I'm not even thinking about optimizing yet. How long did it take you to do all of this?
Took me just 2 days.
2 days for an expert.
That's it.
OK. I got to come clean about something. I was actually testing you this whole time to see if you actually knew what you were talking about and if you were an expert. I ended up building something extremely similar to this in just a couple hours.
Oh, really?
Yeah, and I did it using our internal Ray development agent that we've been building. I'm sure a lot of the audience here has already been using, hopefully, tools like Cursor and Claude to work on their and develop and debug their Ray workloads. But we started to build something internally where, think of an agent that sits on top of something like Cursor, but beyond just having access to your code base, it has access to live documentation, whether it's Ray, Anyscale, or all the other libraries you're using. It has access to a growing and live updated list of best practices to use, anti-patterns to avoid, and also some contextual things like your specific cluster, what resources you have, what are the things you're trying to optimize for, what are the relevant metrics, logs, and events that are important to your workload, and even historical information from maybe prior runs. And using all this, we can actually generate working Ray code where we can test it on a small batch. And yeah, I think this is a great way to actually get started and convert your workloads, debug them, and optimize them.
So anyone can be a Ray expert?
Yeah, pretty much. With the guided observability you showed, the data and MLOps integrations, the whole dev to prod experience, and now with agents on Anyscale that we're going to be rolling out soon, yeah, I really do think that everyone can start to become a Ray expert.
That's great. And all this without having to worry about infrastructure either.
Exactly.
So let's bring back JK to talk about how all the infrastructure magic comes to life.
Thanks, Akshay and Goku. I love Unity catalog integration and lineage tracking. And Goku, we need to talk. I just got a message from our on-call about the V3 final service you launched. All right, so let's peel the third layer, the cluster controller layer. This manages end-to-end compute lifecycle management with sub-minute cluster startup time, upgrades, intelligent auto-scaling, and multi-cloud, multi-GPU features. Governance layers gives you cost controls, budgets, to make sure you're able to scale and keep your finance and security teams happy. Last year, we made 2 big announcements. First was Kubernetes GA on Anyscale. And I'm actually very happy to see strong adoption, 20% month over month. We also made it easy for people in OSS to convert to Anyscale. Today, I'm super excited to announce our deep collaboration with the Google GKE team. Anyscale and the GKE team are working closely to bring the power of Ray and Kubernetes together to envision the AI stack that Robert talked about. We are working on features like label-based scheduling, resource group isolation, in-place pod resizing. This gives you fast startup times for tasks and actors. It gives you better bin packing, improved reliability by reducing OOMs. And on a particular workload, we saw 30% more gains because we scale vertically first before going horizontal. This is a big deal, and we are going to invest a lot more in this area. The second feature we talked about was budget controls. This is a feature that is also getting a lot of love. And today, we are announcing even more capabilities in this area. Resource tags, which makes you easy to do cost attribution, cleanup, and filtering, and a brand new invoicing dashboard so that you can track your costs. Compute efficiency is an area on top of everyone's mind. GPU availability is an issue. GPU utilization is an issue. And we have been hard at work in this area. To talk more about that, I would like to invite Elizabeth Hu onto the stage.
Please welcome to the stage Elizabeth Hu, Product Manager at Anyscale.
Thanks, JK. So this time last year, the industry was searching everywhere for spare GPU capacity. Sometimes there wasn't enough capacity in a region or even in the entire cloud provider, and you just needed to get an H200 wherever you could get it. Anyscale has always been designed to support multiple deployments of clouds, where a single customer can run across regions, cloud providers, or even different compute stacks. So we thought to ourselves, why does an Anyscale cloud need to be tied to one set of resources? Couldn't we look across different resources to see where we could find capacity? To solve this, we're introducing the next generation of deployment, multi-resource clouds, now available in beta. Anyscale takes care of the infrastructure complexities of running multi-region or multi-cloud for you. Anyscale intelligently searches across registered resources to meet your workload's requirements, all with a uniform way to express your resource needs. Multi-resource clouds let you hook up multiple cloud resources to one Anyscale cloud. These can be in the same cloud provider but different regions, different cloud providers, or different compute stacks. Let's say, for example, you really need to get a job done and it requires an H100. Anyscale scans across your registered resources until the necessary capacity required is available to then seamlessly deploy your job. And this is just one more way in which you can unlock flexibility to run AI workloads without worrying about the infra. But now, even if I manage to get a GPU, people are now facing a slightly different challenge. It's not only can I get GPUs, but how do I share capacity amongst my team with competing priorities while getting the highest utilization possible? And GPU reservations sound great until they aren't when those GPUs sit idle while jobs wait in line to run. They also lack awareness of the workload and aren't easily able to burst out of the preset capacity. The result, underutilization, frustrated teams, and wasted budget. Imagine instead a global resource scheduler that understands your workloads, your reservations, and your priorities. That's what Anyscale's global resource scheduler is. GRS lets you effectively allocate and prioritize constrained resources across all RAY clusters across your Anyscale clouds. GRS allows you to create partitions and define rules for all types of compute, including reservations, on-demand, and spot. Let's say your company has invested in an H100 reservation for running training, inference, other GPU-intensive workloads. Now, typically, teams statically partition that reservation, one part for training and the other for inference. But that's inefficient. Inference has to be sized for peak load, leaving GPUs idle, while training jobs sit queued waiting for capacity. Anyscale's global resource scheduler solves this problem by allowing flexible prioritization across all workloads on your GPUs. In my reservation, for example, I'm running a production inference service, and my researchers are launching training jobs. Now, inference traffic can get variable, so one day many more users query my service. GRS is able to preempt lower priority training jobs and allocate those GPUs to inference. And as load increases, we'll continue to preempt lower priority jobs and shift those GPUs over to the higher priority inference service. The other way around, as traffic falls, GRS is able to move those workloads back and resume from where they left off. We can even use idle capacity for some background jobs like data processing to soak up the idle compute. GRS works beyond reserve capacity as well. It can tap into spot and on-demand GPUs. If a job is preempted, GRS can find available compute elsewhere and keep it running. So with GRS, you get higher utilization without sacrificing dev productivity, saving money, and getting you the most out of your reservations. All of this is progress on our goal to support any workload, any cloud, any accelerator. And this is why we've worked to unlock capacity with our partners on AWS, GCP, CoreWeave, and Nebius. However, we wanted to unlock Ray particularly for the enterprise. And that's when our partners at Azure approached us after seeing an uptick in Ray among their customer base. The message was quite clear. Azure customers wanted open source flexibility without cluster management overhead, and they wanted it all tightly integrated into their Azure ecosystem. So we're very excited to announce Anyscale on Azure, now available in private preview. Anyscale on Azure is a dedicated deployment of the Anyscale platform, tightly integrated into Azure infrastructure as a first-party native service. With this Anyscale and Microsoft co-engineered integration, you can manage Anyscale from the Azure portal, pay for it using your Azure commitments, and use Entra ID to manage access controls, directly deploying your workloads on AKS to securely run your AI next to your data. Let me show you a quick demo. From the Azure portal, you can deploy and manage Anyscale as a first-party service, just like any other Azure resource. So under the AI category, I simply select Anyscale to get started. Now let's deploy a cloud. I'll create a new Anyscale cloud, and through a click-through process, all I have to do is assign a subscription, a resource group, choose a region, and give my cloud a name. As a next step, I'll specify cloud storage, where I'll want to grab data from. Under the hood, Anyscale is deploying the Anyscale operator as an AKS extension, so you don't have to manually install Helm charts. And as a reminder, the Anyscale operator manages the relationship between the Anyscale control plane and your Kubernetes cluster. Now, your cloud is almost ready to use. If you needed to, you could also adjust things like access controls, tags, and other settings directly from the Azure portal. And because Anyscale is running entirely inside of Azure's security framework, authentication and authorization happens seamlessly through Entra ID. So as a developer, I'm logging in, and once I've logged in, the rest of the experience looks and feels just like the regular Anyscale UI. For example, I can start up a workspace for interactive development, where I can configure the instance types for my head and worker nodes. Once that's launched, I can start to see AKS pods getting scheduled. And just like any other AKS pod, now I can go to the Azure portal and monitor status and other metrics directly from there. Now, going back to our workspace on Anyscale, I can start to do development for things like a multimodal data pipeline. And here you can see how easy it is for me to start getting working by using data already pre-configured in an Azure Blob Store. So yes, it's very easy to get started in a way that's both scalable and secure from the start with Anyscale on Azure. To talk us through the partnership and how we made this successful, I'd like to welcome to the stage Keerti and Brendan Burns.
Please welcome to the stage Brendan Burns, CVP, Microsoft Azure Cloud Native and Management Platform.
Welcome, Brendan.
Thank you so much.
Great to have you here at Ray Summit.
Yeah, for sure.
Well, you are one of the OGs of Kubernetes, co-creator, co-founder. Your name is on the wiki page. I looked it up.
That's right.
Share a little bit about the early days and maybe draw a parallel to what you're seeing today.
Sure, yeah, I was reminiscing actually about the very first KubeCon. KubeCon's coming up next week. But the very first KubeCon was here in San Francisco in a room about this size about 10 years ago. And you know, that sense of energy and the hockey stick of downloads that you showed earlier, it's very reminiscent of that experience. And so you know, I'm very optimistic that the kind of community that we built worldwide with Kubernetes is the kind of community that's forming up right now. And I look forward to Ray Summit being scaled out in 10 years.
Oh, those are inspiring words, mate. I'm very excited about that as well. Well, you talk in your role at Microsoft to a lot of enterprises.
Yeah.
So maybe talk a little bit about what trends you're hearing when it comes to AI.
Yeah, I mean, I think everybody started out with, we need to figure out how to AI our business, maybe 2 or 3 years ago. And so a lot of it was just talking about, like, what are the opportunities to embed AI into the business. But I think now as we're entering, maybe the real productionization part of it, what we're seeing is, the business is actually what's the most important thing. The AI is in support of the business. And so people are trying to figure out, how do I build the right models in addition to combining them with foundation models? How do I think about cost control? How do I think about security and reliability? And all of these concerns that come with actually shipping something that go out to a banking customer, an insurance customer, these regulated industries. So we're helping people through that, and we think these open innovations like Ray are essential components in how we deliver that platform or help customers build that platform themselves.
Do you see the conversation about should we build an AI platform or should we just call an API endpoint come up?
Yeah, I mean, I think, obviously I'm on the infrastructure side within Azure, and so we talk to a lot of customers in some sense who've already decided they want to build their own platform, but they're thinking about how do I blend a mix. I don't think it's a either or, and certainly our aspiration is not for it to be an either or, but rather a blend where there's going to be use cases, there's going to be prompts that work really well with foundation models where you're paying per token, and there's going to be places where you want to run your own models for fine-tuning or because that's the right cost versus value trade-off, even all the way down to CPUs, or you want to have the same infrastructure at the edge. I think hybrid AI is another area.
That's a good term.
Really
hybrid
critical.
AI is exactly what we're seeing as well. So talk a little bit, in terms of infrastructure, Ray and Kubernetes working together.
Yeah.
How do you see it?
Well, I really think that, I was thinking back to the keynote that I gave, and it was all about democratizing distributed systems. And I think the same thing with Ray, you need to provide, I looked at that decorator that was adding, that was being shown earlier that added RDMA support for communicating with GPUs. That's one line of code, right? I guarantee you there's not one line of code behind that ease of use, right? So providing that ease of use for people to be able to access the core technologies that they need to build the applications they want to build, I think that's a fantastic thing that Ray is doing, and I see the same analogs in Kubernetes.
Awesome. Let's talk a little bit about the partnership.
Yeah.
Anyscale, you called us, I want to say 6 months ago now,
right.
And we've put together this partnership, excited about it.
Yeah.
I'd love to hear your words on it.
Yeah, I think there's two really important parts about any partnership that we do, and this partnership like that. The first is we have to have customer interest, right? There has to be people out there who are already using Ray on our platform or already using the software on our platform. And in this case, we talked to a bunch of customers. They're already using open source Ray, right? But of course, a lot of our customers, and I think every customer, wants it to be supported, wants to be able to call my team and any time of day and get help with it. And so that's where the managed solution comes in. And then also, I think, as a cloud platform, we have an obligation to not just ship our software, but provide the best of breed across the world, and especially in the open source world, enabling people to build software businesses on top of our platforms. And so that combination of customer interest and our desire to build a broad platform led us to the partnership, and it's been great.
Awesome. Microsoft's reputation as a partner is legendary, and we are so excited to be that first-party service on Azure, helping you, supporting you in scaling, and helping you scale your service as well.
Absolutely.
So maybe a quick takeaway before we take a break. You've seen obviously the development of Kubernetes, development of Ray, AI-first companies coming up. What's the takeaway for the community?
Yeah, I think my takeaway for the community here is that I think a lot of people in the room and a lot of people in that first room back at the first KubeCon, you're excited about the technology. You're excited about AI in this case and the details of inference and all this sort of thing. But at the end of the day, the most successful platforms are the platforms that empower the most users. And I see that resonating in what we try and do throughout all of Azure and what I was trying to do when we stepped onto the stage at that KubeCon. We said, I'm really trying to democratize distributed systems. And I think that we've made a lot of strides in that goal, and my suggestion to you and the broader Ray community is if you want to achieve that impact, think about how can you democratize AI out into the world? How can you make all of these tools and techniques that are revolutionizing the things that you're building today available to 10 times the number of developers tomorrow, or 100 times the number of developers in a few more years? And if you do that, you're going to build a really successful community, and you already have. And so I really would take that inspiration around democratizing AI.
Awesome. Well, thank you very much. Really appreciate it. We are inspired and looking forward to partnering closely.
Thank you so much. Have a good day.
So I want to take a moment to recap some of the announcements we made today. Starting with Ray, our contribution to the Linux Foundation obviously was the highlight. Super excited about that, but also support of Ray Direct Transport, RDT, support for RDMA, and deeper integration with Kubernetes, with GKE and now with AKS as well. Anyscale side, the Anyscale Runtime, formerly known as Ray Turbo, with huge improvements to performance across the board, adding observability, deep observability and lineage tracking capabilities on the platform to help developers. Global resource scheduler that Elizabeth talked about, we're super excited about that, and multi-resource clouds, which are emerging as a very important capability for AI companies. And finally, as we just discussed, availability of Anyscale on Microsoft Azure. We are super excited to bring all of these capabilities to you, and it is becoming very clear that there is a new stack that is powering AI native computing, and Ray is at the very heart of it. It's your time to go build a unified AI platform, and we here at Anyscale are here to help with that. I want to take a moment to thank all our sponsors, without whom this summit would not be possible. They're all here in the Ray ground, waiting to engage with you, so when you get a moment in the conference, please do stop over. Next, I'd like to bring Robert back, who will host a panel of innovators that are powering the construction of this new AI native computing stack. Welcome, Robert.
Please welcome to the stage Robert Nishihara, Don Chen, Joe Spisak, and Simon Moe.
Well, thank you all for being on this panel. I feel like this is a rare opportunity because you guys are literally, you three, are laying the foundations of open source AI infrastructure. So for people who don't know, Don is one of the founding team members of Kubernetes. Joe's the product lead for PyTorch. Simon leads vLLM. So we're super lucky to have you here. Here, come sit down. Super lucky to have you, to hear your insights about AI infrastructure and how that's evolving, where you see that headed. So would love to start, with each of you just sharing what you've seen personally with how AI infrastructure is evolving. And maybe Joe, you can start with PyTorch. PyTorch has helped really democratize deep learning. Like, what problems were you initially trying to solve with PyTorch? How has that changed?
Shouldn't it be like us four? I mean, you didn't even include yourself in that. I mean, seriously, we kind of have the stack here, kind of up on stage. This is kind of fun. Yeah, so good to see everyone. Yeah, I think, so the interesting thing about PyTorch is like the goal from the beginning was actually like very narrowly focused on research. Like we focused actually on training efficiency, training speed, like time to experiment, ablations. Like those were kind of like the things that we focused on because it's what mattered to researchers, right? They wanted to ideate, they wanted to explore the space. And so for them, like inference performance, no offense at the time, but like at the time, inference really didn't matter. It was all about training. And
does it matter today, do you think?
I'd say so. Like I think times have changed. I mean, I've been in the space now a long time, and like training was cool and it was important, and it's still obviously important. But like now, it's like inference, like this is the new blood, right? I mean, vLLM is everywhere. It's dominant. It's important for RL, it's important for production, it's important for a bunch of different areas.
It's okay.
But yeah, for us, it was all about like how do you actually like make researchers efficient? And that was honestly the problem we were trying to solve. And like, it's all about Python. It's all about like speed of experiments. So yeah, we focused.
Yeah. By the way, Simon, vLLM is not the first inference engine you've worked on, right? You've been working on inference research for a long time. Can you share a little bit about that?
Oh, yeah. So it was quite great, like previously seeing the rate.
Can you hold the mic a little closer? You might have to just do it manually. Yeah.
The first one to see the rate serve step.
All mic'd up. Great.
And that was one of the early projects that we built here at Anyscale. I was previously working at Anyscale as one of the founding engineers was Robert here, and as well as was a great team here. And at that point, we're working on recommendation system, we're working on regression model, time series prediction, and simple classifiers running on CPUs. And just at that point at 2020, 2019, and then LLM was just the initial ideas. And over the time of 2022 and 23, we start seeing the growth of large language model as an architecture growing from BERT, which was bidirectional at the time, and to decoder only as GPT-2 has shown. And pretty much over time, we're pretty seeing going from CPU-only inference with diversity of classifier and regressor to nowadays large language model powering almost all of the AI stack.
So what changed? Why is inference so central and vLLM so central to AI today?
So what vLLM does is inference engine takes the large language model that's open source or proprietary and run it on data center hardware. You do need the flexibility and performance to run those models efficiently at a lower cost. And vLLM sit at the center, where we bring the most amount of large language model architecture in pure open source, run on the most efficient data center hardwares. You actually do need all of that capability to make sure that we're further lowering the cost of inference while you are really using the capability and leveraging it for the new model and product you're building.
Yeah. And Don, can you share a little bit about Kubernetes? Like, what use cases? It was started before AI was really taking off. So what use cases were you building it for?
Good question. When we first started off the Kubernetes, it is originally designed for the stateless application, right? So those like workload is the informal, and it's really perfect match for the web services and also simple APIs. But however, over the last decade of the evolvement, actually we are basically expansion to support the full spectrum of the enterprise workload from the stateful workload, and while of the concepts of the stateful side and also CSI, and two of the batch and workloads and job workloads, while of the Kubernetes jobs and the queue mechanisms. Those it is the essentially critical for those AI training and inference jobs. Yeah.
So what has that process been like of evolving Kubernetes to really support AI well? What have been the hardest parts?
Hardest part, it is a lot of the concept and shifts, right? So in my mind, there's the three major of the shifts. And one, it is the data locality. And so we introduce a lot of the features, for example, like of the node typology label of the features, which it is enable about the enable like a framework like the Ray, and also other of the framework on top of the Kubernetes. So you can make the intelligent and the typology while scheduling and also the placement decision, and which is allow of the high speed of the GPU to GPU communication. This is one of the major shift. And another major shift, it is we are moved from the services centric of the wheel to the job based of the centric wheel. So we introduce the high level of the concept of the job, and also evolve of the GAN scheduling. So then which it is prevent of the waste of the computer resource, and all those kind of the job have to, like the worker have to start at the simultaneous and or maybe just do nothing. So a lot of those kind of shift, actually it is really critical for us. Also have the performance and reliability and high requirement to Kubernetes. We are working on those kind of things.
Yeah. Yeah, jobs are really fundamental to AI, right? And like Slurm started more from that world, whereas Kubernetes started more from services. Of course, now you can also run Slurm on top of Kubernetes. Yeah. So let's talk a little bit about where you guys see things headed. Joe, maybe you can share, since you helped create the PyTorch Foundation. Like,
Sure.
Why'd you do that?
Why do we do that? Why do we do that? So I think we started the PyTorch Foundation, I guess, now just under 3 years ago. I think that like the conversation actually started probably actually more like 7 years ago when we really kind of merged Cafe 2 and PyTorch and brought the teams together and we created this vision. And I think like ultimately we treated the project as if it was a foundation from the beginning. We wanted as many folks to come together. We wanted to give agency to the community, to code ownership. From the early days, we had the project modularized so that different folks can own different parts of it. And that was really important to us because I think we wanted it to be this durable thing. We didn't want it to be like this cool project, you use it for a couple years, then something replaces it. Like we actually wanted to build it for longevity and scale like from the beginning. By the way, my secret agenda is to convince Dawn to bring Kubernetes into the PyTorch Foundation. We'll see after this panel if I succeed. But ultimately, like we do want to bring in the best of breed, like with PyTorch and vLLM and all these things that people depend on and start to scale up. I mean, Ray is a big part of that, and this stack is, like these are communities I think that are awesome. Like I think the Kubernetes, and CNCF, and I think vLLM is like just rabid, and Ray as well. And when you bring these communities together and they start thinking together and working together and designing together, like I think a lot of these projects are designed a little bit in isolation, and we kind of, as a community and through partnerships, we make them work together. We, there's a lot of blood, sweat, and like pull requests late at night that get these projects to work together and collaborate. But I think like bringing them under some kind of umbrella together and thinking about a vision together, I think is really what I envisioned, and it's starting to really come true. I think like between Ray and vLLM, it's awesome. We want this to be a small set of projects that really are tightly coupled and build the future of kind of how AI is developed and built and deployed and kind of, for not for like just the next year, but really for the next 5, 10, 20 years.
I'm actually curious for all of you, where you see opportunities for collaboration across projects. Like what can we achieve, by deeply integrating different projects that's hard to do without doing that? Simon or anyone,
Sure.
Yeah.
So one thing that vLLM is recently pushing for, where we can see this really cross-stack optimization happening, is that as models are getting bigger and bigger, as you become a lot more capable, you need a large-scale cluster to run inference. So it is no longer the case where you can run the model on a single GPU, not even the case to run the model on a single node, which typically have 8 GPUs. Rather, you actually need to scale it to potentially hundreds of GPUs. As this case, it becomes kind of somewhere between single node inference to training, where you actually need to specialize the serving system, both entirely across the stack from where the API sits, how is the model architected, as well as how does PyTorch and Ray handling both memory management, compute kernels, and down to the Kubernetes side of where do you place each pod and then making sure they all get scheduled and scale elastically nicely. And this is pretty much a cross-stack effort across the entire PyTorch, Ray, Kubernetes, and vLLM stack.
Yeah. Don, can you say anything about how Ray and Kubernetes have been working together or future work we can do together?
Robert, before this panel discussion, and Robert gave all of us something fun to talk. Here is the fun story. Before I started looking into how to support of the Ray, like of the framework, and there's already have some effort on the open source called Kubernetes, right? So last year, I did the same resubmit. I really want to support of the Ray, like evolve Kubernetes and support the Ray natively. So I tried to introduce myself to Ray teams, Anyscale teams last year, but I just failed. So then I get myself a free pass and get to the resubmit last year. And there's the one talk about the Kubernetes. Then after, and one of the speaker, it is from the Anyscale engineer. Then I just hijack a conversation after that because they ask a question, complain about the Kubernetes friction. So then I just give the answer, and I said, how about I provide those solutions? After that meeting, and I stopped at the speaker, and I said, okay, can you introduce me to your leadership and introduce me to your team and the community, he did. And then we started off this kind of partnership on the open source, and also earlier you heard of the Google relationship or partnership. So what I try to say that is I really want to evolve Kubernetes. It is to meet the help support of the Ray, especially of the elasticity and the resilience. Right? Ray is different from the other framework, and elasticity and support. So to support the true elasticities, we have a lot of the ongoing projects. One of the projects is like in-place pod resizing. We recently have the simple of the benchmark, and we found of the in-place pod resizing leverage Ray workload, and we have like the 30% of the performance boost, and to make those work and finish, right? So complete in time. So those kind of things, and we also have like the ongoing of the resize node, which all together and allow of the Ray can be like allow the infrastructure can scale faster ever than the before, right? So the before, and also allow the Ray, and also can take response without of any of the disruption, and for restart. And another thing,
if I can just add on to that, actually, to do a good job with in-place pod resizing, you want to have a good understanding of what's happening inside the container, right?
Yes.
And that's the kind of workload awareness that Ray can provide.
Totally. We try to make of our Kubernetes, it is the framework a while and Ray a while, and the customer metrics, and give the signal to underneath infrastructure. So you could spin up the cluster, expanded of cluster much faster, and also you can take action, right? So to detect of the failure, hardware failure, software failure, and also replace of those kind of things. That's kind of the infrastructure we try to build, also for the resilience, and to provide of the scale, reliable of the foundation, to power like the high level of the distributed framework like the Ray, and also high performance inference stack like the vLLM, and also together with Meta's Monarch, all those kind of things we build of the complete complementary of the open source AI stack. That's kind of the Kubernetes as our infrastructure. I always call myself, and also of the people work on the infrastructure, kingmaker. So we are basically just allow you focus on the high level innovation, and we take care of the rest of the infrastructure.
And Joe and Simon, love to also hear from you, just maybe to wrap up. What's left to do? Is open source AI infrastructure kind of done?
I mean, we're definitely not done. I mean, I think like to Simon's point earlier, I think scale continues to be a theme. I mean, I think when I was first training models 10 years ago in CNNs, like we had a paradigm of training a model, and you could do it on a single GPU, and that's where AlexNet, for example, like single GPU, and then we started scaling up to single machine, and we did distributed, and it was pretty messy, and it wasn't very easy for anyone like besides probably like the researchers or experts to do that. We're now getting to the point where we've kind of like democratized scale to some extent. I think like that part of that is Ray, part of that is Kubernetes, part of that is PyTorch, and like, but we also have like on the inference side, we need to distribute. Like not everyone was thinking distributed inference like a year or two ago. So I think like we still have a lot of work to do in my opinion actually to bring these things together. Numerical stability across the different components is still a thing. How do we actually get more determinism in the system? And that comes with like testing and building these projects more together. And that's, I think, why, again, we build these communities, and that's why we bring these experts together, and these projects get co-designed and co-developed together. So that to me is like, I think, the next stage of where this goes.
Yeah, you just briefly mentioned determinism, but that one word is hiding a lot of work.
It is. It's a huge amount of work in so many parts of the stack.
Yeah, and then just to add on top of that, high throughput and scale is one part. Models are getting innovated architecture-wise every single day, as was new chip is being taped out and experimented. That we're both experiencing in the future of inference is going to be you can go through the highest throughput ever, but also have lowest latency as well. So that you have one engine, one stack, we can go with millions of request tokens per second, but also where when you're using it, it feels instant, snappy, and all the time, always on.
Yeah. Hey, this has been a fantastic discussion. Thank you guys for sharing your insights. I'm always excited to see how much innovation is happening at the infrastructure level. So thanks for your insights, and also thank you, more importantly, for all the great open source work you all are doing. Please join me in thanking Don, Joe, and Simon. Thank you. So I'm truly amazed by the amount of innovation that these three are doing. And it's very exciting for me. It feels like a unique opportunity because they're all contributing, building foundational projects that work together with Ray, and I'm sure all of you are using. So next, we're going to be hearing from Jim Fan at NVIDIA. He's building foundation models for general purpose robotics. And robotics is one of the most challenging, but also most compelling use cases for AI. So I'm very excited to welcome Jim Fan.
Please welcome to the stage Jim Fan, Director and Distinguished Research Scientist at NVIDIA.
I took this picture last year at the MIT Museum. It's a mind-blowing machine built by the one and only Claude Shannon. And this machine uses electric and mechanical switches to solve for the final moves of chess. And I find the naming really fitting. It's called the endgame machine. Because at that time, the world's top computer scientists all thought that solving chess would be the endgame to AI. And then in the next 70 years, Claude Shannon got way more than his wildest dreams. In fact, we beat chess 40 years ago. We solved poker and Go and Dota 10 years ago. And this year, we won a gold medal at IMO and also a Nobel Prize for protein folding. We have made our parents proud. Our AI is on track to master anything that can be reduced to a sequence of strings. So what's left to do? What more glory to capture? Well, here's something that my parents are not proud of. You host a hackathon party on a Sunday, and then you wreck the house. You leave for work on Monday morning, and you come home to a clean house and a candlelit dinner. And yet you couldn't tell if a human or a robot had been there. And that's what I'm calling the physical Turing test, right? It's so mundane, so deceptively simple. All it does is it involves tasks that you take for granted in a messy, unpredictable physical world. Yet I would argue that this is the next, or perhaps the last grand challenge of AI. So how are our most advanced humanoid robot butlers doing so far? Well, trying again, right? It's machine learning. It has to learn. Oh no, catastrophic forgetting. How about cooking? Where's my candlelit dinner? This clip gives me a lot of anxiety, People worry that the robots will rise up against us someday, and I will say, no thanks. I think we're fine for a while. And it's not done yet. It's not done yet. Can it clean up? Oh, brutal. Or I give it, at least it went out like a chimp, right? It went out like a chimp. I haven't not seen a sexier post than that. So why is it hard? Why is robotics so hard? A certain great man said that LLMs are running out of data. Ilya is calling the internet the fossil fuel of AI. What I want to say is, you LLM researchers are so spoiled. You have no idea the pain and suffering that we roboticists go through because we don't even have that data. This is a typical episode that we collect for a robotics training session at the NVIDIA headquarters cafe. And this is what the data looks like if you plot it. It's high-dimensional, continuous robot joint control data. And you can't scrape this from the internet. You can't download it from Wikipedia. And that makes it hard. So how to solve robotics? Basically boils down to two things: the data strategy and the model strategy. And let's zoom in on the data first. We collect data by quite a brute force way that we call teleoperation. Basically, a human operator will wear a VR device, and that streams her hand pose in real time to the robot. So you can control the robot in this way to do the tasks that you want them to do. And here on the right-hand side, it is looking through the egocentric camera of the robot. So as if you're kind of stepping into an avatar, and then make the robot fingers move like your own. And as you can see, this is very tedious, and you hit the physical limit of no more than 24 hours per robot per day. And actually, who am I kidding? It's more like 4 hours per robot per day. And when the robot god is merciful, when they don't throw tantrums, when you babysit them correctly, you get 4 hours. It's not scalable. And if we put it on this data pyramid view, it's really on the top of the pyramid. The real data is high quality, but it has the physical limit. So that's really the human fuel. And then at the bottom, we still have the fossil fuel, because all of these data can pre-train reasoning models and vLLM models. Now, what I'm most excited about is what's lying in the middle. And those are the synthetic data that I'm calling the nuclear fuel, the next generation of what would power the robotics revolution. So the nuclear fuel is infinite in principle, but it's limited by PhD brain cycles because we actually need to come up with novel ways to generate these data, and then GPUs because you are trading compute for data. And the more you buy, the more you save. This message has been approved by my boss. So how to build a nuclear reactor for robotics? This is Eureka, a technique that allows us to train high degree of freedom hands to do tasks like pen spinning. And I want to admit, I'm a subpar human. I can never really do pen spinning. I gave it up since my childhood. I'm very glad to see my AI avenge my poor skills. So how do you get the data to train these complex skills? The answer is there is no supervised data set at all. It's all done by reinforcement learning in massively parallel simulations on the GPU, because very luckily, all the physics equations are basically matrix multiplications. And then running on CUDA, you can run simulations like Isaac Lab to accelerate reality to be 10,000 times faster than real time. Now the question is, how do you transfer this to real? We use a technique called domain randomization, where for the 10,000 environments, you vary their gravity, friction, and weight parameters slightly, and then you follow the simulation principle. Suppose you have an AI model that's able to master 1 million realities with different physical parameters. Then with high likelihood, it's going to zero shot the 1 million and first, which happens to our own physical world. And that's the simulation principle. And then we can apply that to all kinds of robots. We build digital twins of the robot dogs, transfer to real. We're able to manipulate blocks using high degree of freedom hands. And this one is the most interesting. Actually, in Isaac Lab, doing yoga ball simulation is hard. It's bouncy, it's soft. So we didn't even simulate that. But we're able to transfer that to real world. We're roboticists, we're weird, so we just run it in the streets. You know, sometimes I feel like I'm a director of a Black Mirror episode. And after seeing this demo, one of my friends told me that he tried the yoga ball on his own dog, and he couldn't do it. So I'm very proud. We have achieved super dog performance. And then you can scale this up to way more complex hardware, like the humanoid. We instantiate an army of humanoids in Sim, and all of them are going through 10 years worth of training in only 2 hours of wall clock simulation time. And with that much data, we can train a 3 million parameter neural net. Note it's not billion, it's 3 million parameter to control the robot body to stay balanced, walk, run, and jump, and dance. And this small neural network captures the subconscious motor coordination that we humans do all the time. And it's running at a millisecond scale on just an orange GPU on board. So when you visit NVIDIA office, this is shot in the Voyager building, part of NVIDIA headquarters. When you visit us, you might run into these guys running around in the building. Don't be a stranger, say hi to them. And also don't forget to visit our robot hospital. These robots work as hard as our PhDs. No robot harmed during filming. So if we plot simulation data on these two axes, where the x-axis is the diversity, and the y-axis is the speed at which we can produce data, what you just saw is what I call simulation 1.0, the digital twin paradigm, where you build a one-to-one replica of the robot and the world. But that also requires artists and engineers to make and create those replicas by hand. Can we do better than that? Of course we can. We have text to 3D models to generate simulation assets. We have diffusion models to change the textures of the environment on the fly. And you can compose and then generate lots of different layouts. And we can put those together in a hybrid simulation engine that we open source called RoboCasa. And it is an engine that leverages LLMs, diffusion models, text to 3D to procedurally generate infinite variations of indoor environments that you can train a robot in. So now go back to teleop, but instead of controlling the robot to collect data in the real world, we collect one human data in simulation, and we can instantiate it in infinite variety of procedurally generated kitchens. So it can have a lot of visual variety, and we can also augment the motions, the actions, through a process called GR00T Mimic. You start with one human demonstration, you multiply that to n trajectories using environment generation, and then you do n times m, motion generation. And I promise this is the only math you're going to do today. So here on column 1 and 3 are the real data we collect at the lab. And column 2 and 4 are generated through this generative physics engine. So you can see that they still look toyish. You can tell the difference, but they sort of capture the vibe of the real world, right? It's kind of a distribution, a similar distribution, but not exactly digital twin. So we call them appropriately digital cousins. Now, how about this? How about this scene? It's got soft body, right? Fluid, translucent glass, and these very complicated food parts that's almost impossible to describe. How long would it take an artist to create this scene in simulation? It's going to take forever. And if we look at the gaming community, it took them 30 years to go from the left to a photorealistic racing game on the right. Yet it only took the video generation community 2 years to go from something on the left to something on the right. It's still hilarious in 2025, but at least now it's physically accurate noodles. That's important when you get the physics correct. And actually, if you recall, I showed this episode at the beginning. I tricked you. There's not a real pixel in this demo. It's all dreamed up by a video world model, by a synthetic data scaling method that we call GR00T Dreams. How it works is you take a pre-trained video foundation model on the left, and you can fine-tune it on the data that we collect on the robot at the lab. So GR00T Dreams now understands the mechanical constraints and the behavior of the robot. And then you can use it as a neural simulator. So here, the left and the right side start from the exact same initial frame. The only difference is the language. And then we can roll this out. On the left, you pick up the apple and place on the pan, and on the right, you pick up the can and place on the pan. And the video model simulates these counterfactual futures. And because it's a video model, it doesn't care how complex the scene is. So you can have a lot more objects, and it's the constant time compute runtime. And you can pick up the cucumber, pick up the spray bottle. It can all roll out. And then all these lighting and reflection and object mechanics, you don't need a ray tracer. It's all learned through data. And by scaling up the pipeline of GR00T Dreams, we're able to generate millions of what we call neural trajectories to help train the model. And here's something fresh out of the oven. We can push this even further. How about we teleoperate the robot inside a video world model? So these videos you see here are generated interactively and in real time, as if the robots and their hands are moving through a lucid dream. So that's a sneak peek to the next generation of GR00T Dreams based on the NVIDIA Cosmos video foundation models. So I like to think of video world models as Dr. Strange. They have seen almost every possible physical phenomenon from billions of internet videos. So the model learns a superposition of visual realities. And when you prompt it, it collapses the infinite possibilities into one chosen future. And that is simulation 2.0. The neural physics engines. It's soft, it's learned and programmed by internet videos and data instead of graphics engineers by hand. I call them digital nomad, as they wander through the latent space of a diffusion model. So now you have these techniques. Which one do you choose? What's your favorite data? Well, we're roboticists, we're data poor. So unlike Ilya, we can't be picky about our data. We need to integrate all the data under this curve. And we developed a very simple recipe to use this synthetic data integral. Because they all generate into the same data format, you can co-train by sampling from the real SIM 1.x and SIM 2.x pipelines through some weighting functions. And that's it. Incredibly simple recipe. And of course, we show that adding these synthetic data gives you a lot better performance than using real data alone. So note that I'm more than 2/3 through my talk, but I didn't even discuss the model yet. Where's the model? If you take away just 4 words from my talk today, it's data maximalist and model minimalist. So we build very complex data pipelines, but the model is a clean artifact that compresses the trillions of tokens generated by the data pipeline. And this is what our model looks like. It takes directly from photons to actions. And inspired by the work, Thinking Fast and Slow, the System 2 component is a vLLM that does slow, deliberate reasoning and understands language instructions. And the System 1 component is fast and reactive, and we use a diffusion model because the diffusion models are actually really great to generate continuous values like actions. So we basically render these actions at more than 100 Hertz. And putting this together, that's the GR00T N1 Vision Language Action, or VOA foundation models that we built, and this is 2 billion parameters. And we can add different dimensional heads on top of the DIT to adapt to a wide variety of robots. So here is a quick demo of the GR00T N1. Actually, this is N1.5 model in action. So the task is to fetch the healthiest snack, and the robot sees through its egocentric view. It reasons, goes through a reasoning loop, reasons that Apple is the best for you, and then it picks it up. And here's another work fresh out of the oven. We discovered an RL post-training recipe to make VOA models super robust. Here what you see is actually a robot assembling GPUs continuously for hours on end without failure. It's actually almost therapeutic to see these robots tirelessly assemble GPUs. And this task has been approved by my boss. Good boy. Good boy. And we train GR00T on Ray, and we open source the model weights and the fine-tuning recipes to democratize physical AI. And GR00T loves Ray. Why? Because as of now, almost all of our compute jobs are based on Ray. The most important reason is versatility. We need to perform a wide variety of compute tasks, all the way from physical AI, multimodal physical AI sensor data processing, to large-scale VOA training, and to evaluation. And our evaluation pipelines are very complex because we use thousands of different simulation engines and environments running in parallel. So basing on Ray as a single engine for these tasks has made our life so easy, greatly simplified our infrastructure, and I believe Ray has accelerated our progress towards solving general physical AI. Now what's next? As physical AI matures, I believe the world will soon see the emergence of physical API. You know, throughout most of human history, it's these pairs of human hands, manual labor, that rearranges and reshapes lumps of matters into civilization. Now, physical API will, for the first time, offer us a programmatic interface to rearrange the world of atoms. And once we have the physical API, all of the good things, the familiar concepts that people use for LLMs and AI agents will transfer over to robotics. Like we'll have novel physical prompting methods, embodied MCP, and agentic fleet that coordinates a lot of robots to deliver a task. And on top of these, I'm very excited by the concept of programmable factories, where any new product you need, you can program it almost overnight and scale up production. And self-driving wet labs to automate scientific discoveries. And on top of all of that, the physical skill economy, the ultimate app store where anyone can access and enjoy the sum of all human dexterity. So, someday in the near future, you come home from work, and instead of folding laundry or scrubbing dishes, you sit down to a candlelit dinner with your partner, your kids, your parents, and the robots will just fade away into background ambience. And everything is so mundane that you wouldn't even notice. And the day that we solve the physical Turing test will simply be known as a Tuesday. And join us on the journey to the moon.
Please welcome to the stage Devendra Chaplot, founding team member of technical staff at Thinking Machines.
Hi everyone, I'm very excited to be here. My name is Devendra. I'm from Thinking Machines Lab, and today I'm going to be talking about our first product. It's called Tinkr. We launched it just over a month ago now, and I'm going to talk about what it can do for you and how we built it. Great. All right. Doesn't work. Oh, okay. So is. Oh, I see. Got it. Does this work? Okay. Perfect. So I probably don't need to tell you a lot about fine-tuning, the importance of fine-tuning LLMs. Like everybody wants to train their own models these days. For different sorts of applications, customization with your own data, your own products, and so on. And so right now, there are two options of fine-tuning LLMs on two extremes. One is bring your own GPUs, write your own code, do everything, manage everything on your own. And the other extreme is a black box API, where you go and upload a data set and click a button. So what do you have to do when you bring your own GPUs? You, of course, have to go and rent some GPUs. You have to set up CUDA and some deep learning library like PyTorch or JAX. You have to set up some fine-tuning library like Unsloth or Hugging Face or Whirl. And figure out what combination of CUDA, PyTorch, Hugging Face versions are compatible with each other. And even if you get all this to work and you want to now train a larger model, you need to figure out, okay, how many GPUs do I need to use? What kind of parallelisms to use, like data parallel, model parallel, context parallel, expert parallel. What is the longest sequence length I can fit in the GPU memory? When do I use gradient checkpoint? And all these little list of things that you have to figure out on your own. And what this does is basically, it takes maybe hours or sometimes days to set this up and might still be suboptimal, like the performance you get out of it. On the other hand, you have these black box API options where you go to a website, you upload a data set, click a button to train. The problem is that this is very hard to debug. If it doesn't work, you don't know why it doesn't work. It's the main problem, in my opinion, is that it's not interactive. You're not you can't see the loss and the gradient norms go down. And guys, what am I matching? Next one. Yeah. Okay. Yeah, this is good. Yes, good. Awesome. And then it also has a lack of flexibility. You can't specify custom RL environments. You have to kind of condense your data into a JSON-L file and then just upload that. You cannot specify custom loss functions. You can't run tool calls during training, so you cannot hook it up with another environment for reinforcement learning. And for some products, you cannot download the model weights after fine tuning, and like a lot of people want to download their own weights, like and run their own inference or like run it on device and so on. So what we are trying to do with Tinkr is basically find this sweet spot in the middle where you maintain the interactivity and flexibility of training on your own GPUs while abstracting away the complexity of distributed training. So what is Tinkr? Tinkr is basically a training API. It is designed to have these atomic functions like forward, backward, opt-in step, sample, save, load, state, and weights. And the key idea behind this is that we wanted to have an interface which is very similar to what researchers are using within model training labs. And so what you can do is use these functions to design your own training recipe, your own data, your own environments, your own algorithms. And so the way it works is like you focus on your training logic. You specify, here's my training data or my environment, and you can specify your algorithm, loss functions, hyperparameters. And the way you do all of this is like you write a simple Python script. And this runs on your laptop, on your CPU. You don't need to have GPUs to run the script. And you use these basic API calls like forward, backward, opt-in step, and so on to actually run the training. And what Tinkr does for you is it handles efficient distributed training of large models. Like we support around 20 models right now, the Llama series, the Qwen series, DeepSeek, and so on. And so basically you can like train a DeepSeek 3.1, like 671 billion parameters model by just like writing a script on your laptop. And we also handle the reliability, like so any sort of hardware failures, any sort of replays, we handle it transparently, so you don't have to worry about any of this. Of course, you don't have to worry about how many GPUs your training is going to need and what kind of parallelisms you need to use. So all the ML infra is abstracted away. And installing it is very simple. It's just a Python package. So now you don't have to set up NVIDIA drivers or CUDA or PyTorch or like the sampling libraries like vLLM or SGLang. And the training is very simple. You first create a training client. So you just import the Tinkr Python package. You create a training client, and then you use that training client to do forward, backward, and optimizer steps. So whenever you do this, the model weights are being updated. And then you can create a sampling client, which allows you to like save the weights from your training client and create a new sampling client out of it. And you can pass any prompt and get back responses using this. So I have a small demo. Let's see if it works. Like live demos are always risky, but let's try it. Okay, can you guys see this? So this is a simple Python notebook running on my laptop. I have not installed any like special packages or anything. As you would say, like I'm going to import just this Tinkr package. And so you can basically run this. Let me see, I'm connected to the internet. All right, let's see if this works. All good, I think. Yeah, there we go. So it's good. I have the hotspot, right? So you can like just import Tinkr and like get the server capabilities and find the list of supported models. So these are the models supported today. So you can see all the DeepSeek, Meta, Llama series, Qwen series. I'm just going to run this ahead of time so that like we can see the results quickly. But and then like you can pick any model and you just specify the base model using a simple string, and you create a training client for that base model. So here, I'm using Qwen 30B MOE model, and then you can prepare your data set. So again, there's no special packages here. I'm just like literally creating a data like these 7 examples, and this is an example of like what we call pig Latin. You just take the first syllable of a word and put it in the end and add an A to it, right? Like so, this is just like 7 data points. We can basically like write some code here to convert these this data set into tokens, and this is like what the process data set looks like. So you have like the input as the current token, our target as the next token, and weight is basically 0 or 1, specifying whether you want to use that token for training or not. So like all these zeros are part of the prompt, and all these ones are part of the response, right? And then let me just zoom it, make sure it's visible. So once you have your data set ready, you can just run the training using a simple for loop. Like so, basically what you're doing is like you have like this batch of 7 examples, and we are doing like 6 steps of training on this. And so as you can see, the loss is going down with every step of training. And then once you have trained the model, you can just simply create a sampling client and specify your sampling parameters, and you can sample responses. So like here the prompt is coffee break, and this is like 8 responses from the model. So like the model learned some sort of Pig Latin in just like 6 steps of training. And this is all like trained right now in just like a few minutes, right? And the really good thing about it is like you can start training like within seconds. So as soon as you create a training client, you can start training. So if you have like tried fine-tuning your own models on your own GPUs, you realize that it takes like several minutes, sometimes even half an hour to like start your training job. But here you can like do it literally in 5 seconds. And also creating the sampling client from the training is also extremely fast. Within 5 seconds, you can again create a sampling client, start sending in prompts. Great. Why would you want to use Tinkr? So it greatly improves your research speed. We have designed Tinkr to be used for our own research as well. So a lot of researchers internally in thinking machines use Tinkr for running various types of experiments. I talk about one of the biggest benefits is the fast job startup. You can literally start jobs within seconds. You can just change models from 1B to 671B by just changing the base model string. This is extremely simple. If you, again, try to do this yourself, you realize that once you start training like large MOE models, you have to do like multi-node distributed training, and that it gets pretty complicated very quickly. You can also do not just SFT or like supervised fine-tuning, but also reinforcement learning very easily, because you can create sampling clients, create rollouts using that sampling client, and get back the rollouts and specify your own environment and your own reward function. You don't have to worry about accelerators in your training job. For RL, you don't need to worry about your trainer or sampler GPU pools. We also do a lot of work to minimize the KL divergence between the two trainer and sampler replicas. And then the failure recovery is built in. So if anything happens, like if there is an error or job crashes, we automatically reload your last checkpoint, automatically replay all the data that you have sent in. So from a user's perspective, there are no failures. Like basically, you just, even if there was a failure in the hardware in the backend, we manage it for you. We send the queries to another replica and make sure that you get the correct results. And also one big benefit, you can download your model weights anytime. So anytime you create a checkpoint, you can also download it. So you don't have to use the API once after you train the model for sampling. And the second biggest benefit is like it lowers your costs. So you just pay for what you use. We just charge you by tokens, like training token or sampling token. And Tinkr handles the time sharing between jobs. And so if you think about it, this allows us to offer really attractive prices because we are handling time sharing between jobs automatically for you. So if you think about it, anytime you're running an RL job, once you do a step, optimize a step in your trainer pool, you have to transfer this checkpoint to the sampler pool, and while the sampling is happening, your trainer pools are kind of running idle. and you have to wait for the sampling to complete, and then generate the rollouts, compute the reward, and then do another step of training, and then repeat this. And while your trainer is doing the optimizer step, your samplers are idle, right? So it's by doing time sharing between jobs, now what we can do is like while one user is using the trainer pool, the other users can be using the sampler pool. We also have multi-tenancy where multiple users can be using the trainer and sampler pools at the same time. And so this allows us to achieve efficiency much higher than like what you can get out of a single job. And that's why like we are able to offer these very attractive prices. So if you look at these prices, like so for DeepSeek, the cost of training is $3.38 per million tokens. And so if you were training for even like $10 million, it would 10 million tokens, it would be like $33. And if you think about it, like DeepSeek, typically you would require like 64 or 128 GPUs to just train one copy of the model. And 128 GPUs would cost you like few $100s an hour just to like set up the training itself. The challenges of building Tinkr, there's a lot that goes behind it. We optimize for, of course, the ease of use and performance. So we manage multiple model replicas for training and sampling. We manage all the user queues, routing and scheduling between all the queries and the different models the users might be using. We implement multi-tenancy for efficiency. Multiple jobs from multiple users are running on the same replica. And we ensure reliability. We handle the failures, and we also make sure there are no noisy neighbors. Like whenever there is an error in one job, that doesn't impact any other job. And so really what happens behind the scene is that you need 3 different types of expertise in order to build a product like this. So you need the core infra, the traditional software engineering, distributed systems, routing, scheduling, managing queues. You need the ML infra to do the training itself, like multi-node training and sampling, and then managing all these models, figuring out what kind of parallelisms to use. And then you need the ML science, which is a big focus on Tinkr. Is we provide you with a lot of documentation, cookbooks, recipes to make it really easy for people to be able to use this product and like train great models. And of course, we use Ray in the backend for Tinkr. It is used for to easily spawn RL and trainer and sampler GPU clusters to manage all these different pools of GPUs for different models. And of course, you can also use Ray on the client side. So you can use that to manage multiple RL environments on your side, so you can run all these rollouts parallelly. And then we provide a full Tinkr cookbook that includes realistic examples of fine-tuning LLMs. It has examples, so we provide examples of basic reinforcement learning and supervised learning loops, but also more sophisticated recipes on math reasoning, preference learning, tool use, multi-agent RL, multi-turn RL, prompt distillation, and so on. And so you can check this out. This is an open source GitHub repo. And we have more features coming up in the next few months. Tinkr was just launched 1 month ago, and like currently it only supports LoRa or low-rank fine-tuning, and we are adding support for full fine-tuning and then also image input support. So now you can train the vLLMs for robotics that Jim talked about. We have already seen a lot of community contributions. So the Prime Intellect Environments Hub is integrated with Tinkr. So any of the Prime Intellect environments you can easily use with Tinkr to train models. The GEM library for environments is integrated. There was probably a talk about SkyRL today on the open source project to re-implement the Tinkr API. So that means that you can like use Tinkr even without accessing our backend. So you can host your own Tinkr backend and like learn to use Tinkr with that. And we are also opened up research and teaching grants for Tinkr. So if you're interested in using it for academic use cases, you can apply it for grants here. Thanks. You can sign up for Tinkr at this website. And for any questions, please feel free to email me. Thank you.
All right. That's all for our morning keynotes. I hope you enjoyed them. We've got a lot of amazing content and talks today and tomorrow, so please enjoy the rest of the conference.